Hello, in this video we're going to derive the canonical form for the multiple linear regression setting. Now, we're going to cover the singular value decomposition theorem pretty in depth on page 1, and then on page 2 we'll derive the canonical form. So if you're familiar with the singular value decomposition, you could actually skip to page 2. If you want to review or not very familiar, then this will be beneficial. So it is, let's look at the singular value decomposition theorem. And in a playlist that I call Matrix, I have a proof of the singular value decomposition theorem. However, here I'm just going to cover enough to introduce the canonical form in multiple linear regression. So let's let y equal x beta plus epsilon. So this is our standard model. We're going to let x be n by p with rank p. So there's p columns, and all the columns are independent. So then let's let lambda I and vi be the eigenvalues and orthonormal eigenvectors for x transpose x. Okay. And then let's collect the orthonormal eigenvectors into a matrix called V. So now note this is a p by p matrix. So these vectors are p by 1, and then there's p of them because they're orthonormal eigenvectors. It means it spans this space. So let's let L be a diagonal matrix with the eigenvalues down the diagonal matrix. So L is a p by p matrix. So because they're eigenvalue eigenvectors, this property holds in the eigenvector, and then it has an associated eigenvalue with it. Now, if we want to keep them all in matrix form, you can write, this property like this for all of them together. Now, let's let ui be the orthonormal eigenvectors of x transpose, and these are associated with the positive eigenvalues. So I have a video. So this is x transpose x, and this is x transpose. And I have a video that says the positive eigenvalues of x transpose x are equal to the the positive eigenvalues of x transpose. They're actually the same. So the eigenvalues of x transpose, if we just look at the positive ones, then we're going to have these orthonormal eigenvectors associated with these lambda, or the eigenvalues for this. So the eigenvalues of x transpose are lambda 1 through lambda p, which is the same as these up here, and 0, right? And then this 0 has a multiplicity of n minus p, right? Because this is an n by n matrix, so it has n eigenvalues. It's symmetric, so they're all non-negative. It has rank p, that's why there's p positive eigenvalues. And these eigenvectors, because this is n by n, these are n by 1 vectors. So let's and see, it's actually the number 3 video in my playlist Matrix, where it talks about the eigenvalues of x transpose x and x transpose. Actually, it's worth watching. So now let's collect these orthonormal eigenvectors into U1. Now the first p, they're associated with the positive eigenvalues, associated with the positive eigenvalues, and then let U2 be the n minus p other orthonormal eigenvectors associated with this n by n matrix. So then we collect those into what we call U. Now U is an n by n matrix, and it contains all the orthonormal eigenvectors. Now from the theorem, so from the singular value decomposition theorem, U1 takes on this form. Now where x is the design matrix, v is up there, and L to the minus 1/2 is actually it's a diagonal matrix with the square root of the 1 over the square root of the eigenvalues. Now here, so if we right multiply by L to the positive 1/2, that becomes the identity matrix, and it gets transformed over and becomes this. So from here we go to here. And we're going to use this on the next page, deriving the canonical form. But first let's show that U1 are indeed eigenvectors of x transpose. Now U, we said, was of this form, so we plug it in here. But then V is eigenvectors of x transpose x, so that becomes VL. V is eigenvectors, L is eigenvalues. Now this becomes L to the 1/2, but then let's also stick in the identity matrix. So we have x, V, and then this is what the L to the 1/2 is, and then this is the identity matrix. Now we can combine L to the 1/2 and L to the 1/2 to be L, and then this piece here is what we were calling U1. So look, it is an eigenvector, right? And these are the eigenvalues. Now, a few notes here. The column space of X is actually equal to the column space of X transpose. Now this is something we haven't proved in any of the videos, so I may put out a separate video for that. The rank of X is equal to the rank of X transpose. And this is proved several times in many of the videos, and unfortunately I'm not pointing to one here. So the rank of this is P, rank of, right? So we said it has rank P. So if we take a basis, or P orthonormal eigenvectors, this forms a basis for this column space. Right? And then if we take U1 transpose, this is actually a perpendicular projection matrix onto that column space of X. Now I have a video called Perpendicular Projection Matrices that highlights this theorem quite well. So, but since it's a perpendicular projection matrix, if we right multiply X by it, we get X back. It projects everything back into the column space of X. But since X is already there, it projects it back onto itself. So now let's derive the singular value decomposition. So we start out with X, V, and U1 prime. Then we post multiply by the identity matrix, which is this. Now, so this is L to the 1/2, we have that. And then U1 prime, and then this is U. But this is the identity matrix because these columns are orthonormal. So we're just left with L to the 1/2. So now if we right multiply by V prime to this, and then left multiplied by U1, we get this, right? But this is the identity matrix, and this is a perpendicular projection matrix onto the column space of X. So this is X, that's the identity, and we get this. And this is actually the singular value decomposition of any matrix X. So now let's jump right into the canonical form. So Y is equal to X beta plus epsilon. Now we stick in the singular value decomposition for X, and we get this. Now V are constant, so let's just rewrite beta, V prime beta as gamma, and then this comes down. And this is actually one form of the canonical form. Now let's go further though. Remember on the previous page we said U1 V or L to the 1/2 is actually XV. So this is another form of the canonical form in multiple linear regression. Now, technically we could go from here to here, right? Because if we stick in the middle here the identity matrix, V prime, then we have XV, and remember gamma is V prime B. So a lot of books will just derive it straight to here. But I like driving the singular value decomposition because well, you'll see it helps with some of the properties that I'm getting ready to show you. Okay, so now let's expand, let's write out what V is. V is a matrix of the orthonormal eigenvectors, so there's P of them. And these are P by 1 vectors. And then let's multiply that X into these, and so we get this is a vector, this is a vector, we get P vectors, which actually kind of like the original design matrix. There's P columns, right? And there's P parameters here. So here, this is a matrix with P columns, and this is a parameter with P unknowns. So it's actually very similar to the original. But what the difference is, these are transformed, slash rotated axes. The original axes were X1, X2, X3, etc. But now we have new, so we can call it E1, E2 to EP. They're just transformed or rotated axes. And we'll talk more about that later. So the least squares estimate for gamma, and so if this is the model, it's X transpose. So this is X transpose X inverse X transpose Y, right? So that's what we get from here. Now let's unpack this. So let's take the transpose in, we get this. Well, this is the identity matrix, and then that combines to L, and it's L inverse, that's what this is. And then here you can take the transpose in, you get this, which is this, and then this combines to L to the minus 1/2. Now if we rewrite this as, say, Y star, then we get this. And actually, that's another form to write in the matrix in what's called canonical form, is you start pre-multiplying by stuff, either, U1 or U1 transpose, but we're not going to jump into that. So we get this. So now, but if we just look at one of those, say, gamma I hat, that means we need the ith element of this vector, which is y star, yi star, divided by the square root of the eigenvalue. Now if we look at the variance of our least squares estimate of gamma, so we'll work with this one here. So then we take this constant out front, take the variance of y, and we transform it out back, and we get this. Well, this is sigma squared I, so the sigma squared comes out front. This combines, well, that's the identity matrix, and then L to the minus 1/2, L to the minus 1/2 is L in, to the minus 1. So if we look at, so this is a diagonal matrix. So if we look at the variance of one of these, say gamma I, then we want the ith diagonal, which is this, sigma squared lambda I. And the covariance between any two of these gamma parameters is 0, right? Because it's a diagonal. So they're independent, they're orthogonal to each other, which actually makes doing linear regression quite nice, or multiple linear regression. But one note here is if we have multicollinearity in our design matrix, there's going to be a few of these lambdas that are quite small, say less than epsilon, which then is going to make this variance quite large. So it's actually going to be very tough to reject the null hypothesis that that parameter is 0 if there's multicollinearity in the model. Now, one thing to think about is once we come up with our least squares estimate for gamma, which is this, or your this, however you want to think about it, how do you get back beta, right? Well, beta, well, gamma is this. So if we pre-multiply by V transpose inverse, which is actually just V, because this is a matrix of orthonormal eigenvectors. So it seems like if we pre-multiply gamma hat by V, then that should be a pretty good estimate for our original least squares estimates. So let's look at that. And this is the last derivation. So so beta hat is equal to V gamma hat. And I probably should put a question mark there until we prove it, but it ends up being true. And we're going to prove it. So gamma hat was this, L minus 1/2 U transpose Y. That's what we derived on the first page. So now what we do is we're going to, in here, we're going to put the identity matrix, which won't change this. But the identity matrix that we use is L to the minus 1/2, L to the 1/2, right? So then these combine to L minus 1, and then this stays the same. But then in the middle of this again, let's put another identity matrix, V prime V, which is this. So here we have all this junk. We put the identity matrix there. Of course, this was L to the minus 1 and V. Now we start grouping. So here, these three can be grouped into this, right? When you take the inverse in, it gets moved to the front, and it's V prime, V transpose inverse, which is just V. And then this is L to the minus 1, and then this one gets moved to the front, and the inverse of V is V transpose. So this is these three. Now these next three, we can rearrange, we can take out a transpose. And of course, Y stays the same. Now, here, if we split L into L to the 1/2, L to the 1/2, and then stick in an identity matrix, it won't change this. And that's what we do, right? But now let's group these three into this. So they'll take out a transpose there, and then these we leave the same. But each of these are is X based on the singular value decomposition. So we have X transpose X, inverse X transpose Y. Well, that's the original least squares estimate for beta. So we do get our original estimates back by pre-multiplying by V to the least squares estimate for gamma. Well, anyway, that's all I have for this video. Hopefully you enjoyed it. I sure did. I have one more video on canonical form. That's the next video. Hope to see you there. Thanks. Bye.